Okay. So actually it is estimated that until 2050 the overall world will double its energy sources, and those energy sources will be depleted. So it is of a paramount importance to implement, develop, design novel energy sources. And as we always talk about, activated carbon is one of them, and graphene can be the next emerging carbonaceous materials that will be implemented in energy storage devices as well as in energy conversion devices, where when we talk about energy storage devices, then we talk about batteries and supercapacitors. When we talk about energy conversion devices, we talk about solar cells and fuel cells. What I would like to discuss now is the graphene implementation in electrodes and graphene-based supercapacitors. I will talk about graphene powder-based supercapacitors. When we talk about graphene powder-based supercapacitors, then actually we talk about the same processing and manufacturing procedures that we have discussed during the previous lectures, where we have a powdered carbonaceous material, usually an activated carbon, and we prepare with it either via rolling or coating electrode material. So we, in this kind of lectures, actually we will relate to powder graphene as a substitute for activated carbon. A specific emphasis will be given into the graphene oxide or GO-based supercapacitors, because actually these are the most common one that you see in literature, as well as also demonstrated as initial commercial prototypes. After that, I will continue by speaking on about graphene metal oxide hybrids, graphene CNT hybrids. So we are talking now about composite electrode and composite cells, and in the end I will talk about electrochemical supercapacitors based on CVD graphene. So we are talking about thin film or thin layer supercapacitors deposited or grown with methods used in microelectronics, directly attaining the cell and stack structure via the fabrication method itself. What is graphene oxide, or what are those graphene oxide-based supercapacitors? Actually, to attain graphene oxide is done via a very simple method, chemical method, and this is the reason why these are the most common supercapacitors or graphene-based supercapacitors today. We are talking about single sheets of oxidized graphite. This is why it is called oxidized graphene, that they have the property that they have the following properties. First of all, they are not so conductive. Their thickness is not 0.14 nanometer, but is 1 nanometer thick. The surface area, it is approximately 1,600 square meter per gram. So actually it is lower than the 2,600 square meter per gram that we saw in monolayer high quality graphene. But a very positive property is that they are dispersible in polar solvents. So what can you do with this kind of graphene oxide sheets? You can attach to them functional group and create functionalities that on one hand will improve the conductance or the conductivity, and on the other hand they will also improve the surface area and maybe involve some reduction oxidation reactions that will increase the capacitance attained from this kind of material. So why these graphene oxides, even though that they have inferior properties in comparison to monolayer graphene, to dimensional graphene, why do they have become such an emerging supercapacitor electrode, potential electrode material? Because of the cost effectiveness and the simplicity of the fabrication method. What I'm taking here to show you is this Abalonics graphene oxide. Abalonics is a commercial company that produces graphene oxide, and they have two samples. They have the GO and the ASC GO. What is the difference? Of course, the chemical composition. So in the Abalonics GO, we have a carbon contact of approximately 53 weight percent, and the ratio between the carbon to oxygen is 1.8, with impurities of hydrogen and nitrogen at 1.7 weight percent and 0.13 weight percent respectively. The AS6GO product, actually it has a lower carbon contact as well as a higher oxygen contact, so we are talking about more or less the same carbon to oxygen ratio of 1.7 in comparison to 1.8. The hydrogen contact is low, so it is as low as that it cannot be detected via conventional detection methods such as SIMS or absorption methods. And also, actually, what we have in this material is that mainly we have pure carbon and oxygen. These are the atomic force microscopy, the AFM images and profiles of such sample of the Abalonics sample, so one can see the surface area and the profile of the surface. As I said, one of the most promising or most advantageous properties that this graphene oxide layers have or exhibit is the capability to attach to them functionality groups. So one can attach either carboxyl or carbonyl or hydroxyl groups. There are some researchers who have done some research by attaching epoxide groups, and these are the types of most important functional groups that one can attach to such graphene oxide layer. It depends on the position and the location and the crystallinity of both carbon groups and the direction of the graphene oxide layer. So one cannot attach a specific group to wherever one wants, but in out of plane direction you can attach hydroxyls or epoxides. On the edges you can attach carboxyls, carbonyls and hydroxyls, and in the in plane you can have either like species. So how can we do this functionalization? Is it a process that attains higher temperatures, higher pressures, specific conditions? No, actually we are talking about different functional group reactions that can take place at low to moderate to high temperatures, depending on which groups we want to attach to. So if we want to use a low temperature reaction range from 60 to 250 centigrades, we are talking about this kind of functional group reactions shown in the table over here. So we have the carbon to oxygen formation, and then we have a carbon oxygen formation. Look at the links here at the bonds. We have a carbon hydroxide loss and the epoxide loss, and these reactions are shown as a function of the temperatures. If we want to go to moderate temperatures at the range of 250 to 650 centigrades, then we have carboxyl reactions, and to high temperatures above 650, 750 centigrades, we have the remaining carbon and oxygen and carbon double oxygen layers. So these are the data taken from the literature. What are the usual or the conventional graphene oxide synthesis? The conventional synthesis known today is the Hammer methods. Actually, it's a very old technique from 1958, and later on it was modified by James Tour adding a ratio of 1 to 9 phosphoric acid, and a range of others, and these are the most common oxide syntheses that are being used today in order to fabricate and manufacture graphene oxide. So how do they look like, these graphene oxide nanoparticles, or what is the process that we can use in order to fabricate them? Usually these nanoparticles are of a size of 1 micrometer to 1 micrometer to 1 nanometer thickness, with a specific area, as I said before, about 1,600 square meter per gram. And the overall process of graphene oxide nanoparticle formation actually involves 3 stages. First of all is the delamination, then the functionalization, and the reorganization in attaining an overall structure of functionalized graphene oxide nanoparticles. So we have an initial, the graphite source, and the delamination. Actually, it sounds very similar to the mechanical exfoliation that we discussed before. Is done via oxidation. So we take the oxide, we oxidate it, and we attain graphite oxide. And after that, we delaminate the graphite oxide layers via dispersion into attaining these rods of graphene oxides. These rods of graphene oxides can be reducted or functionalized and decorated into attaining new compounds and new products. For example, what I would like to show here is the research of Lobato et al. Being published at the Electrochemical ACTA in 2014, demonstrating us a sandwich-type supercapacitor where you have here graphene oxide electrodes. Within them, it's a coin cell actually configuration with electrodes consisting of graphene oxide, and the electrolyte is an aqueous electrolyte of acidic 2 molar sulfuric acid. What we have here is that we have the capacitance as a function of the voltage. So we can see that the volumetric capacitance of 177 farad per cubic meter are being attained. These are relatively very large values of volumetric capacitance. What it is also shown in this graph is that the reduced graphene oxide conductive spacer, or this RGO, it's an X-ray diffractogram of the reduced graphene oxide in comparison to the graphene oxide. So we have the initial peaks of graphene oxide nanoparticles and the reduced graphene oxide conductive spacers. Actually, the graphene oxide, when we look at the Ragone plot of the graphene oxide versus the graphene nanoparticles, the graphene oxide is the red curve over here, and the graphene nanoplatelets are the blue curve over here. We have the power versus the energy density, the Ragone plot. We see, and in black, of course, it is shown here. What is shown here is the activated carbon. We can see that the graphene oxide successfully competes with the activated carbon in terms of the energy density. And on the other hand, it provides a similar power to that of graphene nanoplates. So this shows actually experimental evidence that using reduced graphene oxide one can actually substitute the activated powder and attain higher energy values. And we are talking about a difference of almost an order of magnitude. It is a huge improvement. Some other examples, actually, what I would like to show here is another research implementing chemically modified graphene, or denoted as CMG, within electrode material. Again, what you see here is the configuration of the electrode of the supercapacitor cell. And you have the electrode material, the separator dividing the cathode and the anode, which are actually deposited or implemented on top of a current collector, and you have stainless steel plate. So actually, if you remember the first lessons that we talked about aqueous configuration, it reminds very much the aqueous configuration stacking or designing mode, and not the rolled one. But what we have here is that the electrodes are not consisting only the active material, only the chemically modified graphene, but they also consist of binder, and the binder here is a polymeric based one, the PTFE binder, and the BET done on this chemically modified graphene electrodes actually showed a surface area of 705 square meter per gram. We are talking about a low surface area, so let's say very similar to a low-cost activated carbon. Here you have the transmission electron microscope images showing the individual graphene sheets extending from the CMG particle surface, and in B you have low and high modification of scanning electron microscopy images of the CMG particle electrode surface. At C, as I said, the configuration of the cell. These supercapacitor cells were in the size of 1.6 centimeter discs with an electrode thickness of 75 micrometer. They were tested in a variety of electrolytes. First of all, an aqueous alkaline KOH electrolyte having a cell voltage of 1 volt. We are talking about, they were also tested in acetonitrile solvent and as well as in the PC, in the propylene carbonate solvent. Both those solvents have as we discussed, have a higher cell voltage of 2.7 volt. And specifically the capacitance that they were tested via using cyclic voltammetry technique. We will talk in another series of lectures regarding the measuring methods, and cyclic voltammetry will be one of the most common methods used, especially in the first stages when we want to evaluate the electrode material. What you have here in this cyclic voltammetry graphs, you have the specific capacitance. Actually, it is calculated via the current versus the volt. One can see here what is the electrochemical stability or the electrochemical window that is related to the cell voltage in this kind of voltammograms. Here what is shown is the voltammogram attained while using an alkaline, a KOH electrolyte, because you can see that the upper limit voltage is 1 volt due to the electrolysis. The capacitance values for this aqueous-based graphene, chemically modified graphene supercapacitor was 99 farad per gram. This is the capacitance of a single electrode per weight of CMG material of the single electrode, where for an organic electrolyte it was 135 farad per gram for an aqueous electrolyte and 99 farad per gram for an organic electrolyte. So it's completely a substitute of activated carbon. For aqueous media or aqueous-based supercapacitors, these kind of values of 135 farad per gram, these are very known values, even when you use activated carbons, but not activated carbons at the 700 square meter per gram area, then you have a lower specific capacitance, so by let's say 20 or 25 to 30%. What is interesting to see is that the capacitance for organic electrolyte based supercapacitors is relatively high. Usually with commercial activated carbons, you attain in organic supercapacitors capacitance values of 70, 75 farad per gram. So this could be indeed a substitute of activated carbon as an electrode within a supercapacitor device. What I would like to show here is another research done by an it was done a little bit earlier, at 2010, by Wu et al. And what they have researched are the composite films of chemically converted graphene, CCGs denoted, and polyaniline nanofibers, PANI, that they were prepared by vacuum filtration and mixing mixing dispersions of both components. So what we are talking now about hybrid or composite electrodes. So we do not, up to now we talked about electrodes consisting only either graphene oxide or graphite oxide material or chemically modified graphene. Now we are talking about composite electrodes, that they have composition of where the graphene is the main matrix, and then you have some embedded components. In our case here is the polyaniline nanofibers. So this composite film has a layered structure. We are talking about a layered, laminated structure, and those polyaniline nanofibers are sandwiched between the chemically converted graphene. So this is what you see here. You see here the layers of CCGs with the polyaniline nanofibers embedded and sandwiched within. Here, for example, what they did, they built this kind of cells with this sandwiched electrodes, and they tested them via charge-discharge. What you have here are the common charge-discharge graphs of the voltage versus the time. And in black you have the CCG itself. You can see that it has a very typical supercapacitor behavior of a charge and discharge curve. On the other hand, what you see in blue and green are the flexible composite films with somehow distorted charge-discharge spectra. So you can see that the IR drop here is more pronounced than in the common CCG based supercapacitor. Somehow in the blue curve, they appear to somehow overcome this kind of hurdle and then decrease the IR drop by doing some kind of functionalization. So the supercapacitors based on this conductive flexible composite film showed a capacitance of 210 farad per gram at a discharge rate of 4.3 ampere per gram, and they were tested in an aqueous 1 molar sulfuric electrolyte. So another fabrication method, synthesis method, talks about having graphene oxide and doing another kind of treatment. We talked about delamination, we talked about the oxidation, after that we talked about the delamination, after that we talked about the reduction or the chemical modification, and now what we are talking about is another route that has been shown here by a group in Singapore. We are talking about the graphene oxide that goes through a microwave treatment, and then it has a chemical activation in the alkaline environment, KOH environment. After that, you wash and dry it, and then you have what is denoted as an alpha modified graphene oxide. So this schematic flow chart actually shows the microwave exfoliation and reduction of the graphene oxide, and the following chemical activation of the microwave enhanced graphene oxide with the KOH that actually creates pores, as you can see over here, while retaining the high electric conductivity. So what is important here is to see that this kind of activation actually the same that we saw when we talked about the activation process of carbon material. Again, here it was done on this graphene oxide in order to enhance the pore structure and the surface area. Actually, this, as I said, this is a research done in Singapore by Zhou et al. In 2011. And what they did, they measured, again, what you see here is a cyclic voltammetry. They measured the capacitance and versus the potential, and actually they measured it while using an organic electrolyte. You can see that the maximum voltage here is 3.1 volt. What is important to understand that via this fabrication or synthesis mode, they managed to attain a very high surface area of 2,400 square meter per gram. And actually it is almost reaching the theoretical limit of graphene at 2,600 square meter per gram. So they tested, they tested 2 electrode cells and tested them at even cell voltages of 3.5. Somehow the cell voltage is also extended, so the electrochemical window is enlarged, probably due to the functionalization and due to this and due to the specific electrolyte that actually it is being used here. It is not a pure acetonitrile electrolyte, but it has also the implementation of some specific salts in order to prolong or to extend the electrochemical stability of the electrolyte itself. It's an ionic liquid in the end of the day, so what you see here is the extension of the cell voltage at 3.5 volt, and not only that, but the specific capacitance attained in this kind of cells was 200 farad per gram, which is a huge capacitance when you take under the consideration that you use, first of all, an ionic liquid mixture of organic solvent, and this high capacitance value does not result not only from the high surface area values that was attained via the KOH activation process, but it was attained mainly due to the macro size, or let's say pore distribution attained in the graphene oxide flakes or layers. So for the packaged cell, the specific power and specific energy were 75 kilowatt per kilogram and 20 watt hour per kilogram respectively. So when we are talking about this kind of values, that they were not attained only for electrode materials per se, but they were attained for the overall cell configuration and cell design, then actually it is a very nice achievement. We attained 20 watt hour per kilogram. It puts us real closer to a conventional lead acid battery, and we are talking about a very, very small device over here. And the capacitance, actually it's 75 kilowatt per kilogram. It's 1 order and magnitude higher than the current supercapacitors that are being used today. So actually this could be a very promising technique for substituting the current activated carbon with this novel graphene-based material. So up to now we talked about basically graphene-based electrode materials. The next section will focus on the graphene metal oxide hybrids. And actually, metal oxide-based electrodes generally suffer from very poor electrical conductivity. I will go, we did not talk yet about pseudo-capacitors and hybrid capacitors in this course. This will be the next lecture, but and probably I will go back to what I'm going to say here also in the next lecture. But usually what we have here, we have a hybrid configuration of a supercapacitor when one electrode contains a carbonaceous material, mainly activated carbon, in our case graphene, and the other one consists of metal oxide material, namely in a nanostructural form, and these metal oxides are not as conductive as the carbonaceous material that serve today as mainly electrode material. So one has to find out some ways in order to improve the electrical conductivity, and this kind of hybrid electrodes could be a path to attain that kind of conductivity improvement. So to fully utilize all the potential advantages of graphene and pseudocapacitive materials, much effort has been devoted to the studies of the composites of graphene and pseudocapacitance materials. When we talk about pseudocapacitance material, we're talking about this kind of metal oxide materials that and why it is called pseudocapacitance, because we are not talking about the simple electrical double layer capacitance attained via electrostatic charge mechanism, but we have, in addition to that, also the capacitance attained via reversible reduction oxidation processes. So what are the knowledge that is attained up today in terms of these graphene metal oxide hybrids? We talk about the high surface area graphene that can, why in the end of the day to implement graphene? First of all, we have the high surface area graphene that can induce the uniform growth of nanomaterials on the graphene surface. As we said in the beginning of the lecture, the graphene is a two-dimensional layer, which is a very large one in terms of the XY axis, so it can reach even micrometers in terms of the size. So it is very easy to implement or to attach or to grow uniformly nano materials or nanometal oxides on the graphene surface. So the electroactive nanomaterials deposited on the graphene surfaces, they suppress the aggregation and the restacking of the graphene. One of the hurdles that one have to overcome in order to achieve high quality graphene monolayers is graphene layers in the end of the day is to know how to prevent them from restacking one above the other. So this is the reason why, for example, the properties, advantages decrease with the number of the graphene layers, and it is not that simple to somehow prevent this kind of aggregation of one graphene layer to the other. And this way can be, and the deposition of nanometal particles or nanometal oxide particles can be a way that will prevent the aggregation and the restacking of the graphene layers. So in terms of the configuration, one can think about a novel design or a novel configuration of let's say, sandwich supercapacitor or battery cell, where one layer is the graphene, and it can serve as the conventional anode, and the metal oxide deposited on top of it can be the cathode. And here you have a pseudocapacitor cell, and you can go on and stacking, and on one way having the benefit of preventing the aggregation of the graphene layers one above the other, and on the other hand you will have the benefits of having a pseudocapacitor device with enhanced electrochemical window and probably enhanced capacitance as well, and overall enhanced energy density device. So what will be another benefit of that kind of novel configuration? it will be the high conductivity of graphene that will enable very fast electron transport through the underlying graphene layers to the electroactive nanomaterial layers. So another benefit is the great mechanical flexibility of graphene that will improve the cycle stability and the rate capability of this composite electrode for supercapacitors. Because as we'll probably discuss on the next serial of lectures when we'll discuss about the hybrid capacitors, what the drawback of this kind of capacitors is the limited number of cycles. So if one knows how to overcome this limitation, then one can benefit from both the high energy density and the high cyclability or cycle life. What I would like to show here is exactly what we talk now, but in a more schematic and visual way in order to make it easier to understand the design the design of this hybrid graphene metal oxide electrodes. So so this is actually taken from the research, late research of 2013 from Peng et al. And what did they do? They used manganese oxide manganese oxide as a pseudocapacitance or the nano metal oxide active material, and graphene sheets. We are talking about planar graphene sheets or hybrid sheets based on hybrid nanostructure of ultra-thin manganese dioxide and graphene sheets, denoted here as MnO2 GMCs, using a gel electrolyte of PVA with phosphoric acid. You have to take under the consideration that when we talk about this kind of sandwich devices, one has to think in terms of not liquid electrolytes, but one have to think about solid state electrolytes, and this is and the gel is a good example of that. So what we have here, we have gold electrodes, and each actually supercapacitor cell is printed, and here you see how much it resembles the microelectronics fabrication mode with the solid electrolyte between those electrodes. So these hybrid films were prepared by using vacuum filtration of the manganese dioxide graphene solution. And what you have on the right hand over here are the electrochemical behavior graphs of capacitance versus the current density, and the Ragone plots of power versus energy density. And you can see that the hybrid configuration showed improved electrochemical performance compared with the graphene, with the only graphene-based device. Here you see this is the graphene-based device, and this is the hybrid pseudo device. And you can see that the capacitance was increased by a factor of almost 4 if we go to higher current densities. And we have a specific capacitance of 267 farad per gram at 0.2 ampere per gram. And you can see that it did not decrease that much with the increase of the current density by an order of magnitude. At 10 ampere per gram, we still attain 208 farad per gram. So what you see here is a very good rate capability demonstrated while using this kind of sandwich structure. What is important to see is that what happens after a certain number of cycles. And what they did, they tested 7,000 cycles, and actually this is not a sufficient number of cycles, but nevertheless we are talking about research that was done in the university. So what they see a 92% capacitance retention after 7,000 cycles. So, and we'll talk about the parameters that actually will define what will be the desired cycle number. It depends, of course, on the application, but just as a thumb rule, as a rule of thumb, one can have the end of life being defined as a 20 to 30% capacitance deterioration being denoted as the end of life. So still we are very far away from the end of life. We have only 92% capacitance retention, but after 7,000 cycles, so it looks good. This is all one can say at this stage. 7,000 cycles are not a sufficient cycle life, but nevertheless, this is a very promising research that can be further explored and maybe improved, and in order to be implemented in a specific device. And what makes it very attractive? This is clearly shown in these Ragone plots of power density versus energy density, where you have the EDLCs, the known electrical double layer capacitors, the pseudo-capacitors, and the lithium-ion batteries. They are somewhere here. So we are talking about energy densities at the range of 10 watt-hour per kilogram, with power densities of 10,000 watt per kilogram, so 10 kilowatt per kilogram. Very nice values, actually. So a very promising route for being implemented and shown in a real device. So again, there are a lot of there is another research done even earlier by Cheng et al., also involving manganese dioxide being coated on top of the graphene, and using it in a graphene metal oxide hybrid supercapacitor. What we have here are the schematic illustrations of coating of graphene with manganese oxide nanoflowers. You can see the coating on top of the graphene electrode, and the schematic asymmetric supercapacitor with the graphene as anode and manganese dioxide coated graphene as cathode. This is the scanning electron microscopy image of the manganese dioxide coated graphene. It shows the graphene nanosheets indicated by these arrows here, and what you see are these kind of nanoflowers are the manganese dioxide particles on top of the graphene sheets. So graphene was explored as a platform for what these examples and these research samples come to show us is that graphene has been explored as a platform for energy storage devices. This is a case where graphene is decorated with flower-like manganese dioxide structures fabricated by electrodeposition method. The specific capacitance was measured in a neutral aqueous electrolyte, potassium chloride, 1 molar electrolyte solution, and what they have attained is a 245 farad per gram for graphene thin film, and with the coupling of the manganese oxide decorated graphene cathode, the capacitance increased to 328 farad per gram, a very nice number. If you translate that number to the specific energy of manganese oxide coated graphene, we attained 11.4 watt-hour per kilogram, and the specific power was 25.8 kilowatt per kilogram. So these are values that are above the higher limit of the commercial supercapacitors today in terms of the specific energy density, especially when we talk about aqueous-based supercapacitors. Okay, now another hybrid configuration that I would like to focus about, it involves the graphene and CNT hybrid configuration, and what we are talking now is about a three-dimensional configuration that can be attained via using a variety of fabrication techniques or cost-effective synthesis methods, where what you have here, you have a building block, you have a three-dimensional configuration or structure where the initial building block consists of a layer of graphene with carbon nanotube pillared structures on top of graphene layers in a way that you can attain this kind of three-dimensional configurations. And the methods that one can fabricate this kind of architecture are chemical vapor deposition. This is the most usual known one. Electrostatic spray deposition. In this method you have less control in the method, in the parameters, in the process parameters, such as the growth rate, the deviation between each carbon nanotube and its location within the three-dimensional architecture. One could use also wet solution and vacuum filtration methods or an anodic arc discharge. Again, the most controllable method today is the chemical vapor deposition. Why are these kind of three-dimensional architectures positive or advantageous? First of all, because you attain a greater surface area, and not only a greater surface area, but also an enhanced structural strength due to the mechanical strength provided to the structure from the carbon nanotubes pillars. In addition, on top of that, as we discussed before, graphene monolayers have a very good in-plane electrical conductivity, but a relatively low out-of-plane electrical conductivity. So having pillared CNTs structure dividing from each layer of graphene, besides avoiding the aggregation and restacking of each layer in similar to what we saw when you put a layer of nano metal particles sandwiched between such kind of graphene layers. Here, in addition to that, you attain not only good electronic conductivity, but also good ionic permeability, good ionic conductivity as well. So this kind of configuration actually possesses desirable out-of-plane properties while maintaining the advantageous in-plane properties. So it could be an ideal structure for the addition of chemical functional groups like biomoleculars, polymers, and other materials, and it can open a broad area of electrode design in terms of nano design. What I would like to show here is actually some implementation of such an idea, such a graphene CNT hybrid. It's again the research done in Singapore by Wang et al. 2014, a very late one, where what we have here is the schematic fabrication of reduced graphene oxide CNT hybrid. On B this is a top view, and the C is the cross section taken by scanning electron microscopy. What you have here are interdigital microelectrodes. Again, we are talking now about thin film 3D architectures attained via the same microfabrication methods that you see in microelectronics. So what we have here is the silicon or the silicon oxide, the wafer substrate. You have the titanium gold electrodes, the omnicoat mask, and the electrode material. So what you attain in the end of the day, these are interdigital microelectrodes that are used here, that are used and shown schematically here. So what are the methods being involved in such kind of process? First of all, we have an electrostatic spray deposition and photolithography that should be applied in order to fabricate those interdigital microelectrodes. What is the novelty here is that they are using binder-free electrodes containing this kind of hybrid composite of graphene and CNTs. what they did demonstrate is that the addition of the CNTs between the sheets of graphene sufficiently increased the accessibility of the electrolyte ions between the stacked RGO sheets, and in this way they improved the energy and power density. So the specific aerial capacitance was 6.1 millifarad per square centimeter. Now we are talking about microelectrodes, so the range of farad is, of course, it is reduced. So we are talking about 6.1 millifarad per square centimeter at a low scan rate and 2.8 millifarad per square centimeter, having an overall stack capacitance, but look at the size of the stack, of 3.1 farad per cubic centimeter at a high scan rate of 50 volts per second. So this micro device had a low time constant of 4.8 milliseconds and energy density of 0.68 milliwatt hour per cubic centimeter and a power density of 77 watt per cubic centimeter. What we talked about now are actually values that we were not familiar with those before. We are talking about values of orders of magnitude, but please take under your consideration that we are talking now about microelectrodes. So we are and when you compare these kind of microelectrodes to what you have today in the market, usually done by either ceramic plates of thin plates of ceramic oxide material like titanium oxide, etc. These are very, very large values. These are values higher by an order of magnitude in comparison to what you have here today for commercial micro supercapacitors. So electrochemical capacitors based on the CVD graphene, what we talk about is having an ultra-thin planar supercapacitor based on pristine CVD grown monolayer of graphene on some polycrystalline copper foil. These are the common substrates of graphene growth, and or multi-layer reduced graphene oxide film. This kind of design, actually, it's shown here. It is a well-known design of a supercapacitor with the cations and the anions going to both electrodes. Here you have the stacked geometry, here you have the planar geometry. So the in-plane design, what is interesting to understand here, that while having a fabrication mode like the CVD gives you quite a freedom in order to design your cell as you want. You can have either an in-plane design or an out-plane design, depending on the materials that you use and depending on the plates and the surface that you have. So the in-plane design, in the in-plane design, the surface of each graphene layer was exploited more efficiently for energy storage. Since it exploits we are talking about the planar geometry shown here, because it exploits efficiently the surface area. Those planar MSCs are very favorable for electrolyte ions to interact with the whole surface of the graphene sheets while having a very short diffusion distance. So the performance of this kind of device was examined in both PVH, phosphoric polymer gel electrolyte, as well as in an aqueous 1 molar acidic sulfuric electrolyte. And what they attained are specific capacitance values of 247 farad per gram, approximately 80 microfarad per square centimeter for the CVD grown monolayer graphene film, and up to 394 microfarad per square centimeter for the multi-layer RGO film. So another example of this kind of thin film micro supercapacitors is the research of Neo et al. From again 2013. You can see that these kind of researches are very current research because this has become an emerging area of application. And here they show the schematic fabrication of reduced graphene oxide on a substrate by combining both photolithography with electrophoresis. So these optical images of the RGO pattern on a PET substrate with an gold film and is shown here in B. And in C, what they have is the MSC on a PET substrate. You can see that these substrates are flexible. So again, we are talking about flexible devices, flexible electronic devices. And the graph over here shows the specific capacitance versus the scan rate of these RGO MSCs in comparison, shown here in blue, in comparison to conventional supercapacitors here in red. So one can see that in the end of the day, here you attain flexible, ultra-thin, and all solid-state graphene-based MSCs with this phosphoric PVA gel electrolyte. The fabrication methods are the methods known in the microfabrication of semiconductors, photolithography, electrophoretic deposition. These are well-known techniques, and because of the short ion diffusion pathway, the resulting RGO MSCs exhibited a high specific capacitance of 286 farad per gram, which is 3 times higher of that of conventional RGO-based supercapacitor with an approximately 86 farad per gram. Another research, which is actually a very unique one, because all the others they involved costly CVD techniques or microfabrication techniques. This research being done by El Qadi from Santa Barbara, I think, University, or San Francisco, I don't know, somewhere in the western part of US. What they have done here is using a light scribe DVD drive, using a laser reduction of graphite oxide film in order to produce graphene. And this is a very simple mode. It's like you have a DVD and you could scribe on that via lasering, and this is a very cost-effective method in order to produce such kind of enhanced supercapacitors or microcapacitors. So they used this picture here actually shows the schematics of the fabrication process for this laser-scribed LCG, laser-scribed graphene. And you can directly write the LCGs with more than 100 micro devices on the same disk. So what we are talking about is the laser reduction of graphite oxide films to graphene. It's the same oxidation and the reduction of graphite oxide, but here the oxidation method is done via laser reduction or laser writing. So it is done directly by a standard light scribe DVD drive. So after laser reduction, these graphene-based materials can be used directly as electrodes of supercapacitors without any need for binders, without any need for current collectors. So what you get is the whole effective area of the whole material that you already, of the whole graphene material that you already scribed on your disk. So what are the properties? This looks very nice, and they also tested that. And the surface area by this approach was measured as approximately 1,500 square meter per gram. A very large surface area, and in terms of the specific capacitance, the capacitor showed a capacitance of 265 farad per gram in an organic electrolyte. And of course, due to the operation of, due to the utilization of an organic electrolyte, you have a wide operation window of maximum 3 volts. So this is a very innovative and very interesting and cost-effective method of having this kind of micro capacitors or thin layer capacitors on top of deposited without any binder, without current collectors, directly on top of a CD. Another thing that actually was shown in the latest graphene conference was and actually this is the first commercial use of graphene supercapacitors that we know today, is this ZEBCO charger that was developed and built by ZEBCO. And this is supposed to be the first commercial charger based on graphene supercapacitor technology. It was supposed to be launched it is supposed to be launched on Christmas this year. Let's hope and see whether they will do it. Actually, there are people who say that this is the new StoreDot, or StoreDot is the new ZEBCO. I don't know. It depends on which will be launched first. But nevertheless, the concept is more or less the same. What they do promise, I don't know what StoreDot promises, but what they do promise is that a 5-minute charge will cram approximately 1,500 milliampere of charge into the graphene supercapacitor, which according to the claims of ZEBCO will be enough to completely recharge an iPhone and 75% of the battery in an iPhone 6 or Samsung Galaxy S5. So this is something that is being these graphene-based supercapacitors are there is no argue that graphene will open a new area, a new age, and it will be the carbon age or the graphene age, and there is no doubt that it's a good thing, it's a very positive thing. Let's hope that it will be, and the sooner the better. And we are confident that graphene has a key role to play in the green technology economy, and as I said, the next couple of decades are at least envisioned to be the graphene era. So if one could look how the evolution of materials during the civilization have evolved from the flint, wood, and metals we have in the mid last century, we went into plastic and silicon, and now people see graphene as the next thing, as the next coming thing. So it has a lot of opportunities. It is a very exciting material and it is and the novelty is there. So it waits for us to research and to develop. So.